So let's pick up our journey. There is a PowerPoint on Teams, which is entitled Non-Specific Immunity Macrophages. Okay? So this PowerPoint is on Teams as well. And what we're going to talk about in this particular session is a macrophage. What is it? Where does it come from? And what does it do? Okay? So those are the things we're going to talk about in this particular session. All right. So let's have a quick look. Everybody excited?
Yes.
Say yes, Dave.
Yes, Dave.
With feeling, please.
Yes, Dave.
I didn't hear anybody saying it wasn't good.
Yes, Dave.
Thank you very much. Wonderful. So, we talked yesterday about how we keep pathogens out of our body. But some of you might have been thinking, that's great, Dave. We know how we keep pathogens out of your body, but what the hell happens when they actually get in? What happens when they get in past our mucociliary escalator? What happens when they get past a break in the skin? What happens when they physically enter our bodies? Is it game over? Or is there something else which is effectively going to address that pathogen once it's broken into our bodies? And of course the answer is yes. And that's where this thing called the macrophage comes in. It is a cell. It is a cell that is capable of moving within your body. It is a cell that is capable of moving within your body to the site of an infection. However, it is still non-specific. In other words, it is engineered to address or tackle any type of pathogen that gets into your body. So it will have a go at getting rid of a bacterium. It will have a go at getting rid of viruses. It will have a go at getting rid of protozoa. It will have a go at getting rid of absolutely anything, including cellular debris if you've been injured, or even dust. So this thing is basically an enormous cell that can physically move around your body, which is capable of basically getting rid of anything that shouldn't be there. So it's kind of a cross between a soldier and a refuse collector. It basically just gets rid of absolutely everything that's there. So if things get past our defensive systems on the outside, this is the first thing that they're going to encounter when they get into our bodies. Everybody okay with that so far? Right, brilliant. So don't panic. We have got this wonderful thing called a macrophage. Now you do not have a little tiny marine running around inside your body, but ostensibly a macrophage is kind of a soldier. A macrophage is basically an engineered Terminator type of, like a soldier kind of thing. They are there to get rid of things that should not be in your body, okay? And they are incredibly good at doing it. So this is kind of a computer-generated image of a macrophage. It's supposed to be kind of 3D, because the scale of this actually is kind of wrong when you look at it. The macrophage is this big kind of blobby thing that you see over here, and this kind of hot dog down here is supposed to be kind of further out towards you. It's supposed to be kind of 3D-ish. And this is a bacteria. So you can kind of see the macrophage kind of engulfing this bacteria. And we'll talk about the process as to how they do that in the next few slides. So before we actually get into the macrophage itself, I think it's kind of important that you have some history, that you have some sort of context as to what the hell these things are and also where they come from. Macrophages are made in your bone marrow. So they are cells that are made in your bone marrow. And they're formed through what we call differentiation, which just means that these cells in your bone marrow change shape and develop. So effectively, they're made in your bone marrow, and macrophages are formed through the differentiation of what we call a monocyte. Now, have you all heard of white blood cells? People heard of white blood cells? White blood cells, basically as a correction at this level, we can kind of call them monocytes. So So your white blood cells in your bloodstream are called monocytes. Those monocytes, as we know, circulate around your bloodstream. But when we get an infection outside of your bloodstream, as those monocytes leave your bloodstream, they change into a macrophage. So as they squeeze out of your bloodstream to go towards the site of an infection, they change from a monocyte, which is inside your bloodstream, to a macrophage, which is inside your tissues. In other words, they leave your capillaries, squeeze out through the gaps, and go towards the site of the infection. So when they leave your capillaries, they're called macrophages. When they're inside your capillaries, they're called monocytes. Are people okay with that differentiation of terms? Brilliant. Okay. Now, where do we find these macrophages? I've already said that they're made in your bone marrow. They circulate around as monocytes inside your bloodstream, but it's kind of important, they've got such an important role that your body has decided to position them strategically all over your body. So as well as circulating around your bloodstream, your body has positioned these macrophages in areas where they anticipate there may be a problem. So you have macrophages right now, you have them in your lungs. You have macrophages in your connective tissue. You have macrophages in your liver. You have macrophages in your kidneys, even in your brain. Now we give them different names. So they are called alveolar macrophages in your lungs. They're called histocytes in your connective tissue. Kupffer cells are in your liver. Mesangial cells are in your kidneys. Microglial cells are in your brain. And osteoclasts are in your bone. Irrespective of the fact that we give them different names, they are all macrophages. And they are all strategically placed to deal with problems that your body anticipates may come their way. So instead of having your army all in one place, what you've done is you've created a series of bases around your body where you position your troops based on the fact that this is where you might get a problem. In other words, you're shortening the distance and the time these things have to move around. Okay? So they are strategically placed to deal with infection. Okay? Macrophages. Brilliant. So, what do macrophages do? Macrophages are big eaters. They are literally big eaters. They are some of the largest cells that you have in your body, and yes, they are capable of moving. But the most important thing for you to remember is a macrophage is an enormous eater. It has a huge appetite for things that are not supposed to be there. Okay? Now, as we will see, they do not have eyes, they do not have teeth, but they basically consume any debris inside your body that should not be there. So if a cell gets damaged, these will eat the damaged cell. If a bacteria gets into your body, these will eat the bacteria. If a virus gets in and is clumped together with antibodies, as we'll see, these will eat the virus. They will eat anything. They ain't vegan, they ain't vegetarian, they're not lactose intolerant, they will eat anything. They are not fussy eaters. People got the idea? They'll literally eat anything that is not supposed to be inside your body. Okay, so this is kind of an important slide because I'm about to introduce a word to you that you definitely need to use in your handbook when you are completing this particular piece of work for me. And the key word is this word. Now the Americans say phagocytosis. Over here we kind of say phagocytosis. It doesn't matter which way you pronounce it as long as you actually use this word because it's an important word. I'll explain what that word means. We know that our macrophages are big eaters. In fact, they are literally cell-eating machines. That's what they are programmed to do. A cell that will consume other things inside your body that are not supposed to be there. In fact, their name literally translates from the Greek as being big eater. Okay? They will eat bacteria, they will eat cell debris, they will eat anything. But as I have said, they do not have eyes, they do not have teeth, they do not have a mouth as such. So how the hell do they eat these things that are not supposed to be there? They literally, it's kind of like a horror movie, they literally engulf any viruses and bacteria. They literally surround the bacteria or the virus and literally, like a horror movie, form a stomach around it and then dissolve it. Now briefly, we're going to see this in a little bit more detail, this process of them basically engulfing the bacteria or virus we call phagocytosis. So the process by which they engulf the damaged cell or the bacteria or the virus we call phagocytosis. Okay. And effectively, as we were saying there, it surrounds the bacteria, it consumes it, it brings it within itself, it forms a little tiny primitive stomach around the bacteria, then it will dissolve the bacteria, and whatever debris is left behind, it literally just gets rid of. Boom. That process that I've just described is phagocytosis. So let's look at that in a little bit more detail using this slide. Okay. Here we have our macrophage. Inside the macrophage, we have some little, what we call vesicles. These are tiny little, you can think of them as plastic bags packed with enzymes. Enzymes that are there to basically dissolve anything that this engulfs. Okay, so they're a very powerful group of little tiny enzymes. Here we have a virus, but equally it could be a bacteria. And you can see in stage 2, the actual macrophage, and we'll talk about this in a second, has sensed the presence of this particular virus and is now moving out what we call these pseudopodia. It's now moving out from its membrane and is starting to engulf the bacteria or the virus. By this time, it's virtually game over for this. Stage 3, the virus is now encapsulated in what is effectively a small primitive, you can think of it as a stomach. So it's now inside the macrophage, completely surrounded by another membrane as an envelope forming a primitive stomach. You'll then see on stage 4, that little primitive stomach is now joined by that little sac of enzymes that were in the lysosome. Those enzymes now completely digest the virus or the bacteria, and eventually, in the final stage, all the debris, which is no longer threatening to you, is literally excreted from the macrophage. Now, the one thing about this slide is, it kind of shows you the process of phagocytosis. Do not be confused. A macrophage does not do this one at a time. In other words, it doesn't just have the capacity just to form pseudopodia to take in one bacteria. This thing can eat 50, 60, 70 bacteria at a time because it can form this primitive mouth anywhere along its surface, depending on where it actually senses those viral particles or bacterial particles. So unlike us, it doesn't just have one way in, it has numerous entry points at which it can actually grab these pathogens and get rid of them. Okay? And that process is phagocytosis. This is on your handouts. This is the diagram that you are going to complete for me that shows that you have an understanding of phagocytosis. Okay? So this slide basically gives you the information that you will transpose onto your diagrams and resubmit back to me so that I can see that you have that knowledge of what phagocytosis actually means. Okay? And again, the narrative for this particular diagram and also all of this is something that you would label for me. Okay? So it's all there for you. All I've done is draw you this diagram because I know that it's not a test of people's artistic ability, okay, to be able to do this, but effectively a lot of the information that you're going to show me that you understand is on that slide. People okay with that? Okay, brilliant. This is an actual macrophage. So this is a scanning electron microscope study of a macrophage literally engulfing bacteria. So here's the bacteria down here. All of these will end up being literally engulfed by this huge macrophage. Okay? It's going to take him literally 50, 60, 70 at a time. These are some of the largest cells that you have in your body. Still can't see them with the naked eye, still can't even see them under a normal microscope. Not particularly well. So you need something quite big, but these are literally the biggest cells that you've got in your body. And the important thing is they can move. So right now, unpalatable as it may be, you have got these things literally moving all over inside your body, looking for debris and looking for pathogens to get rid of all the time. They never rest, they never sleep. They're literally cleaning up anything that's got in you that doesn't need to be there all the time. So I suppose a critical question is, if they haven't got eyes, how the hell do they find these pathogens? What is it that leads them to these pathogens? And basically what happens is, when those cells in your body become infected, when those pathogens get into your body, both the pathogen and your cells will send out a chemical message. And that chemical message basically shouts to your immune system, help. And we're going to look at these messages right now, okay? So, the process, and it's kind of an important word, the process by which our macrophage, illustrated here by our hound dog, okay, our macrophage basically follows a scent trail towards the pathogen. So just like a hound dog, a macrophage basically follows a scent trail. That scent trail is established primarily by the cells in your body screaming out a chemical message that says, help, I'm being infected, send help now. It's a chemical message that they send out, okay? And these macrophages can sense that chemical message and they will navigate their way towards the actual damaged cell. Have you all kind of played that game as kids, or maybe it's one that I did when I was much younger, which is like you're blindfolded and so you have something and it's you're hotter, you're colder. You know, you're colder, you're colder, you're colder. No, you're warmer, you're warmer. No, you're getting hotter, hotter, hotter. Bill's getting worried. Hotter, okay. It's kind of like that game. Macrophages play that game. They follow a scent trail. The more scent there is, the closer they are to the pathogen. So the hotter it gets. And they basically follow that scent trail until it leads them to a pathogen. The process, the name that we give to that process of them following the scent trail is chemotaxis. And that's kind of an important word I need you to use when you're completing the assignment. I need you to show me that you understand that chemotaxis is the process by which they move towards the actual pathogen or damaged cell. So if chemotaxis is the process of moving towards the actual damaged cell or the pathogen, what the hell is it that is being released that basically allows this process to go on? Chemotaxis is the process by which they move, okay? the chemicals that are released, in other words, the ones that we said, oh yes, you're hotter, you're hotter, you're hotter, the chemicals that are released are called chemokines. Chemokines. Called chemokines. Chemokines are a general classification of chemicals that are released by bacteria and also predominantly by damaged cells. These chemicals are released when those cells are being attacked by a pathogen, and literally they scream out, help. When those chemicals are released, the macrophage follows that scent trail by chemotaxis, which leads them towards the actual pathogen itself. So chemotaxis is their process of moving, but what they are following are chemokines, a general classification of chemicals released by cells which literally say, help, help now, I'm being attacked by a pathogen. And they're the ones that basically attract these particular macrophages. Brilliant. Brilliant. So, when are they used? We know that macrophages are used when your cells scream out for help. Okay? We know that they release chemokines, the chemicals that are going to attract these macrophages to the site of the infection. So, if you've ever had a splinter, and if it has ever been painful, hot, and swollen, your cells have been screaming out for help. So anybody that's had a spot or a splinter that has become hot and painful and swollen, that is a direct result of these chemokines being released, which are attracting macrophages to the site of that particular infection. And in fact, you know this by another word, which is inflammation. So when a spot or a splinter gets hot and swollen and painful, your cells have been screaming out for help. It is the chemokines that those cells have released, attracting the macrophages, that has indirectly caused pain, heat, and swelling. So basically, when you get a spot or you have a cut, if you do not get pain, if you do not get heat, and you do not get swelling, then there is something wrong with your immune system. Because these are the natural consequences of these chemicals being released by damaged cells to attract macrophages, the result of which what you feel is inflammation. So you're going to ask a question.
Those chemokines it says chemicals sent into the bloodstream by the invading bacteria.
Yes. So basically anything that's been damaged at all, like a cell or a bacteria, will release a chemokine. Those chemokines will diffuse into the tissues around the site of the injury. Some of those chemokines will also diffuse into the blood capillaries themselves. So it's a good question. And we'll see what those chemokines do right now in terms of inflammation. Because, I don't know if you can see that on there, there is somebody's toe. Somebody's toe, and you can see all of this stuff. What do we call this stuff? It's pus. Okay. Having a look at that particular toe, does that toe look hot? Does it look red? Oh, sorry. Do you think it is hot to touch? Yes. Do you think it is painful? Yes. Can you see evidence of swelling? Absolutely. In other words, you have all the hallmarks of inflammation. But the point is, you have got inflammation because you are attracting macrophages to the site of the infection. What do you think all that pus is actually made of? It's actually made of macrophages that have migrated to the infection and have died battling the pathogens that have actually got into your body. So pus is basically millions of macrophages that have died, sacrificed their little lives in order to try and keep you safe. So if you have a client or a patient and you do not see this kind of thing happening, then it's kind of problematic. Now let me give you an example very quickly. Does anybody here look after, maybe in like adult social care setting, somebody who is either type 1 or type 2 diabetic? Yeah. Do you all know, I'm sure you do, that you cannot go near their feet to cut their nails? Do we all know that? Do you know that you cannot go near their feet to cut their nails? Do you know that you are constantly looking for bed sores or pressure sores? One of the reasons why you need to be acutely aware of this is because for those individuals, predominantly who are elderly, who are type 1 or type 2, diabetes will affect not only the nerves in your peripheral nervous system, in other words your pain receptors, but they will also affect your capillaries. Which means if your clients get a bed sore or an abscess or a cut, they may not get inflammation. And if they don't get inflammation, it means your macrophages are not going to the site of the injury, which means the wound gets progressively worse. Has anybody ever dealt with like a leg ulcer or a foot ulcer before? You do know that if they progress, that can lead to amputation because they do not heal. One of the reasons why they do not heal is because type 2 and type 1 diabetes interferes with blood supply to your actual feet. In other words, blood supply is restricted. If the blood supply is restricted, even though the cells in your foot are screaming for help, those chemokines are not going into the capillaries, and those monocytes are not changing into macrophages and going to the site of the injury. And people can lose their foot within 6 months because the wound simply will not heal. Just digress slightly, but it kind of shows you the importance. Inflammation is a positive sign that your immune system is actually working. So, in terms of how do we explain your inflammatory response, let's go through it stage by stage. There's only 4 points we need to know. Here we have, in stage 1, damage to cells. These cells have been damaged here because of maybe a splinter. Bacteria have actually got into this area here. As a result of the pathogen getting into that area, the pathogen and the cells that have been damaged have now started to release chemokines. Those chemokines are going to start diffusing around this area, and eventually they will reach their nearest capillary. When they reach their nearest capillary, these chemokines are going to do something which is really interesting. They're going to start to make that capillary dilate. In other words, the capillary is going to swell. It's going to start to get bigger. If you have got more blood flow into this area, can you see now why that site looks red? Because you're getting more blood going to the area because the capillaries are getting bigger. They can hold more blood in that area. As well as actually getting bigger, the capillary then also starts to become more permeable. Does anybody know what I mean using that word permeable? What does permeable mean? Anybody know what permeable means? No? Great. It means if it becomes more permeable, it means things can get in and things can get out more easily. So permeable literally means things can get out of that capillary more easily. So not only does the capillary get bigger, it also means that things can get out of that capillary far more easily. Now, so you can kind of think of this capillary now as having more little holes in it. which means that plasma from your blood, which is basically water, is now going to seep out of that capillary. Can you now see why that would mean that the area becomes swollen? The reason why it becomes swollen is because the plasma from your blood has seeped out of the capillary and has gone into the surrounding tissues. Red, because you've got more blood flowing. Swelling, because you've got more water from your blood literally leaving the capillary, going into the surrounding areas. The reason why the capillary gets bigger, the reason why the capillary becomes more leaky, is that you want these monocytes, these white blood cells, which are in here, you want them to leave, and you want to allow them to get through these tiny little holes in the capillary to follow that chemokine trail all the way to the site of the infection. So the redness and the swelling are a byproduct of getting your macrophages to where they need to be. And once they get there, they will then completely consume all of the pathogens that have got in through that wound. They will remain there and they will die there. And that is why, if we go back, you see this. Because what you are looking at here are those macrophages that have died trying to save you from that pathogen. So if you see pus at a wound, it means your immune system is working. It means that you have got those chemokines that have been released from your damaged cells, and it means that your macrophages have actually gone to the damaged area and are now basically destroying the pathogen. It means your immune system is working. You should be far more concerned as clinicians if somebody has a wound that does not show signs of inflammation, because if that is the case, then something is going seriously wrong. Okay. So just to recap, we've talked about the macrophage, one of the largest cells that you have in your body, a cell that is capable of moving, a cell that is an eating machine. It will literally destroy pathogens that have got into your body. And the process by which it destroys them is called phagocytosis. We've closed by talking about inflammation. Inflammation, you now know, is a byproduct of actually getting the macrophage to where it needs to be. Okay? And that's where we'll leave this particular part on macrophages. Everybody okay with that? Say yes, Dave? Yes, Dave. Hang on a second, we have a question. The heat, okay, so if you've got more blood flowing into an area, the temperature in that area will go up. So heat is a byproduct of more blood flowing into the area. Redness is a byproduct of more blood flowing into the area. Swelling is a byproduct of the plasma leaving the blood going into the infected area. But don't forget, inflammation is a byproduct of getting a macrophage from here to where it needs to be over here. If we don't see inflammation, something is going wrong with your immune response. Any more questions, guys? The swelling is a byproduct of plasma leaving the blood. Plasma is leaving the blood because those capillaries are becoming more leaky. They have to become more leaky to actually get those big macrophages to squeeze through. Any other questions, guys, before I close down? Brilliant. Well done.